Can you tell me what we will have in each shift register?
And the mic 000 would be transferred to the sensor. So it will become 000, and 1010 it will be transferred to the microcontroller.
No, first clock cycle. I'm talking about the first clock cycle. First clock cycle. We have 4 bits. Each clock cycle we will have a shift by 1. Each clock cycle we will have shift by 1. So I will need 4 clock cycles to complete the shift for those register. So first clock cycle, what do we have? This one will come here, and the 0 will go here. So it's rotating. The one, if I tell you I have this number 0101, do a shift by 1, this direction. So if I shift this direction by 1, what do we get? 0101, shift by 1. What do I get? I will get 0, 0, 0, 1, 0. If I shift again by 1, what do I get? I will get 0, 0, 0, 1. Yeah, if I shift again by 1, what do I get? I will get 0, 0, 0, 0. Right? But because we have this line, we are not going to lose when we shift by 1. This 1, we are not going to lose it. And this 0, we are not going to lose it in the next shift. And this 1, we are not going to lose it. They will go here. And then it will be shifted. And the 0 here as well, we have shift in the other side. The 0, we are not going to lose it. It will come here. Do you understand? So each clock cycle, I will put basically what we will have in each one. So we will have first clock cycle, we will have 0, 0, 1, 0. And here we will have 1, 0, 0, 0. Do you get my point? The first clock cycle, the first shift. Each clock cycle, we have shift by 1. So 0, we will get 0, 0, 1, 0. And then this one, we are not going to lose it. It will go here. So this will become 1. Right? And this 0 will come here. The next clock cycle, second clock cycle. Again, we will have 0, 0, 0, 1. And here in this in the microcontroller side, because this 0 will go there. So we'll have 0, 1, 0, 0. Third clock cycle, we'll have 0, 0, 0, 0, because those will come again here. And then here we will have this one will go to the next microcontroller. It's rotation. As I told you, it's basically we are doing rotation. It's 1, 0, 1, 0. Fourth clock cycle, sorry, I cannot, fourth clock cycle, we will have 0, 1, 0, 1, and here we will have 0, 0, 0, 0. So at the end, after 4 clock cycles, what we had in the sensor is in the shift register of the microcontroller, and what we have in the microcontroller is in the sensor.
Doctor?
Yes.
Why is it? Why do we need to send the data from the microcontroller to the sensor?
Why do we need to send data? This is how it works, and you will see examples later on. Some sensors, for example, I can give you a scenario where you need to send data to the device or to the sensor. Some sensors, they provide more than one value. So it has more than, let's say, more than one shift register. So you need to select which shift register you need to read from. And for this type of devices, the master sends first like a command or the register number. I want data first from this register. So it will tell the device from which register it needs to read, and then it reads the data.
Okay.
Do you get my point?
Yes.
So, and again, now in this case, as I showed you here, it's not important. But for a master to get data, it needs to send the data. And the data could be dummy data. In this case, it can be any data. You can send any data because it's not important. Is this clear? Right?
Yes.
So, back to this one. So this is what I was explaining. And as you can see here, do you see here as well those arrows? As I told you, for example, usually we work with sensors in the embedded system. So if I connect a sensor, the sensor keeps providing data, right? I mean, it needs to keep updating the shift register. Internally, inside the sensor, the data is being updated in parallel. I mean, we don't have serial, so to be fast, we just put the data in parallel. So this shift register accepts data. We can write to it in parallel. When we say we, the sensor will write to it in parallel. And then we can transmit, the data can be transmitted serially. Once data is being transmitted, new data cannot be written until we finish the transmission. And then the same from the master side. Once the data is received, I can read it in parallel. So you can have a variable, for example, x, where you can assign to it the value of the shift register in one go. Do you understand? So we transmit one by one, but once we have the data inside the microcontroller, then that's it. We can just read it in parallel because we work from inside. This is why we have, so it's possible to read and write from the shift register in parallel internally. But you send the data outside, it needs to be serial. So do you see how many lines do we have here? We have the clock. And this clock, as you can see, is an output from the master, and it's an input to the slave. So clock is an output from the master as an input to the slave. We have this line as well, serial data in, which is an input to the master, and it's an output, serial data out. It's an output from the slave. We have as well this one, serial data out from the master, and we have, it's an output, and we have serial data in, which is an input. So do you see how many lines we have? We have 3. As I told you, so it's not just basically one line. We have 3 to perform serial communication. So if you go and buy a device that's, supports serial communication, you should have at least those 3 lines. And the same from the microcontroller. If the microcontroller supports not all of them they support. So if your microcontroller supports, which is the case for the embed, then we need at least 3 pins. So I'll give you more details later on about those pins and how do we work with them. I think this is what I was explaining, for parallel, and about the pins. So we talked about this in the previous slides and in the whiteboard. The circuitry for the master is usually placed within the microcontroller, so we talk about this. The slave might be another microcontroller, so you can have 2 microcontrollers connected together. One can act as master and the other one can act as a slave. And I will show you an example later on if we want to connect 2 embeds together and send data from one to the other. So we will have an example later on. Or it could be, the general scenario or the normal scenario is 1 microcontroller and many sensors, slaves. The hardware circuitry that allows serial data to be sent and received and interfaces between the microcontroller CPU and the outside world. And we mean by the outside world is connecting the devices, other devices, external devices. We call it the serial port. So basically we have the microcontroller, those 3 pins, So, and the hardware circuitry that we have here is called the serial port. Several standards or protocols have been defined, for serial communication, and can be applied by different devices. The most known one is USB, so the universal serial bus. If you say this supports USB, which means you can connect any USB to it. Once we talk about standard or protocol, I mean, you cannot come with a different connector and say this is USB. You cannot come with a different number of pins and say this is USB. We know it's a standard, it's fixed. We know how the connector should look like. We know exactly how many pins we have inside USB, and we know exactly, how the data is transferred between the two devices using USB. So everything is defined. And the same for SPI, everything is defined. So if you want to design a new device and you want it to work with SPI, so you can connect it to SPI, you need to follow the standard. You need to comply with the standard. And so the SPI, which is the serial peripheral interface, is a simple protocol that has had a large influence in the embedded world. So it's used a lot, and you will see this. So SPI is a serial data protocol which operates with master-slave relationship. So it operates with this, with what I explained here. So it follows exactly this. There are other things that I'm going to talk about. One, a master initiates communication and select a slave device. Data can be transferred in either or both directions simultaneously. So once you select when we say select a slave, this means you can connect several slaves to your microcontroller, but you cannot get data from all of them at the same time. You need to select one at a time and read the data from it, and then you can go and select the second one, and so on. How do we select? We'll use we have an extra pin. So in addition to the 3 pins that we talk about, we have the CS, or chip select. I will show you an example later on. So a master must send a byte to receive a byte. I put here byte, but of course it's data. It will be data. Because data could be 4 bits, could be 8 bits, 16 bits, depending on your device. So we send a dummy data. Any data you send from if it's not important what you need to send from the microcontroller, you can just put any data. And of course, the most important thing is to get the data in the sensor or the slave to go to the microcontroller. So this is the most important thing. So we have, for this protocol, we have 4 pins. I mean, 3 pins, the ones that we already talked about them, which is the serial clock. So the clock from the master. So if we talk about microcontroller, we have S clock, serial clock, which is an output. We have master data out, slave data in. This is another output, master out, slave in. And we have master in, sorry, this is an input, master in, slave out. Those are the pins that we talked about before. So those 2, they go to the shift register, and then we have the clock. Plus, we have CS, which is an output again from here. From the master, CS is an output. So we have 3 outputs, 1 input. If we go to the slave, if you buy a slave from the market, a sensor, and it supports SPI, so it should have CS here as an input. So CS is an input. So the microcontroller can put the 0 or 1. The microcontroller can select the chip. So which means it will enable it first before it gets the data from it. And then we have